Yeah, okay. So our next speaker would be Carl. We'll be talking about algorithmic ambiguity.
Hi, yeah. So I'm going to present on some ongoing work with Mikhail Mironov, who's in the audience, and Aram Eptiker probably gets here later today, and then by Marcus. Um, yeah. So the topic is trying to understand ambiguity using Solomonov induction. Um, like in certain kind of predictive situations, there can be sort of ambiguous generalization, and often people have some kind of informal definition of ambiguity or uncertainty or ignorance, and we'll try to kind of quantify this using by investigating how Solomonov induction deals with kind of in situations of kind of ambiguous prediction. And this builds on some recently introduced quantities in algorithmic complexity and probability, which from kind of initially introduced by Wyeth and Pavlovic, which are called the stopping probability and stopping complexity. And there's been sort of a small but growing literature on this over the last recent years. And with sort of the ideas behind this talk, pretty heavily inspired by some recent work from Aram Eptiker and Michael Cohen, which was actually motivated by AI safety. So kind of the formal content is to study when the circumstances in sequence prediction when conditioning on some history or some kind of partial prefix of a sequence causes the posterior universal distribution to sort of return to as if you hadn't conditioned on anything. So it's sort of like you kind of return to sort of the same sort of like state of ignorance that you started out in before you saw the sequence. So that's sort of how I think of ambiguity in the setting of algorithmic probability. So you sort of forget the situations that sort of cause you to forget everything now. And it turns out you have to. It's kind of maybe a bit more appropriate to kind of sharpen this by saying rather than returning to the unconditional universal distribution, you at least work lies on the history. So sort of anything that you know about the past can kind of be used to inform your predictions about the future. You sort of have access to the past, but you don't use it to rule out any possibilities. So you have like so this is kind of relating these two senses of conditioning in algorithmic probability. Yes.
How is this related to the Markov novel or?
Yeah, I mean, actually, I'll talk about this a little bit. So, I mean, there's some connection to the fact that sequence prediction can be non-stationary in algorithmic probability, right? So if you sort of end up in some situation that you've kind of not sampled before, then then this is kind of when you return to ignorance.
Is there an AIT version of their analog?
Yeah, I just don't. No, yeah, not really that occurs to me. Because you sort of don't have this. I guess you can think of this as sort of characterizing the degree to which things are very far from being Markovian, but this would be sort of this would be sort of an inexact statement. Yeah, okay. So then I put some preview of the results of a notation that I haven't defined yet. So it's expected to understand this, but sometimes it's nice just maybe subconsciously condition you to know sort of where things are going, which is some lower bound sort of characterizing the ambiguity of a situation, which I call the fractal inequality, and then some bounds on the coefficient, which we'll get to later. Yeah, and I believe that there will be a later talk, which will go into some detail about how ambiguity can be sort of making agents cautious about ambiguity can sort of have applications to AI safety for agents in general environments. And I, because of time constraints, sort of won't talk too much about this, but you should be probably the best informed audience that that has ever listened to Michael Cohen's talk later in the seminar. Yeah. I just kind of give you the technical toolkit for this. Okay, so let me. So first, I'll talk a bit about ambiguity. What I mean by this. So this will be the philosophical part of the talk. So if you like math but not philosophy, then you can kind of ignore this part. So there won't really be any prereq. But if you like philosophy but not math, then self-explanatory. So so sort of what makes a situation ambiguous. So I mean, first of all, what do I even mean by this? So my motivation is sort of to to partially understand sort of when should we generalize cautiously, but like kind of the real inspiration is this. There's often these like claims from decision theorists and sort of academics, economists, and stuff that there's these two different types of uncertainty. There's sort of uncertainty where you have some sort of ability to put probabilities on statements. You have some maybe you have some sort of statistical information that you can use to estimate probabilities. And then there's situations where you're sort of completely ignorant, where the situation sort of doesn't justify any kind of probabilities and sort of anything goes. And that's sometimes called ignorance, sometimes it's called Knightian uncertainty. And yeah, sort of as a Bayesian, this seems unappealing because probabilities. It seems like your choice behavior sort of always forces you to express some subjective probabilities, and certainly we have this kind of universal prediction method of Solomonov induction from algorithmic probability, which doesn't seem to have sort of distinguished between these two types of uncertainty. So it should be possible to kind of resolve this. To sort of resolve this like apparent difference and kind of understand the sorts of things that people like to talk about as being sort of inherently ambiguous in the context of Bayesian sequence prediction or Bayesian learning. So that's sort of my motivation. Okay, but what does it mean? So what does it mean for a sequence to be sort of ambiguous? Like intuitively, it just means that it's like novel. You've sort of never seen it before, so your prior knowledge sort of doesn't inform your predictions. You sort of don't have enough. You haven't been equipped with enough knowledge to predict in some novel situation. In machine learning, we might say that some situations out of distribution. So that would mean, actually, I think it's just a fancy way of saying sort of the same thing. You haven't seen any samples from this distribution before, so you don't have any statistical ability. So that might be the ML understanding of ambiguity. And in fact, this is often where we see some misbehavior from AI systems, is when they're sort of pushed out of distribution, maybe by some adversarial. Yeah, and okay, then from sort of like the learning theory standpoint, maybe you think of this as being more about non-stationarity. So when you've been predicting a sequence for a long time, you always kind of have a lot of samples, but if the distribution switches, then maybe you don't have any samples from the new distribution. Okay, but I'd like to be more quantitative about this. In some sense, the current date and time is always novel. If the clock has never read 10:55 on this particular date on this particular year, etc. So every situation is kind of novel, and we still expect to be able to generalize and predict the future in most situations. And this is in the same sense, sort of everything's out of distribution in some sense, because there's at least some sort of factor that is changing. And from this is the motivation to AI safety is sort of that when we have some AI face some ambiguous situation, where maybe we haven't kind of imbued it with enough knowledge to behave reliably or appropriately. We wanted to sort of behave cautiously and maybe defer to a user or so. But at the same time, every situation is like somewhat ambiguous, and we don't want the agents just constantly be paralyzed by indecision, which is a problem that I also face. So yeah. So some examples. So but there's many situations where sort of confident generalization is preferred. So for the sun has risen every morning so far, so it'll probably rise tomorrow, even though tomorrow is a new day, so it's also not guaranteed. People often use like the Faucian principle or whatever. If one user asks for coffee in English and then sort of been reinforced that this is like it's a positive reward to give the user coffee, and then the next user asks for coffee in Greek, probably it's like pretty safe to generalize that at least if you've had also some training on the translating between English and Greek, you sort of should be confident generalizing that also make that user copy. But there's some other sort of you apply sort of exactly the same principles and you get some bad results. So it's just superficially exactly the same sort of thing. I've never died before. This is like one of the most consistent facts about my life. But so it seems like by Laplace's rule, I should predict that I'll also survive taking cyanide. This is presumably false. From the third person perspective, it seems obviously false, right? But I've never experienced myself dying, so yeah. Similarly, so if a user can press some, this is a common for AI safety problems like reward hacking, right? So the AI does something good, and then you press the button, and then the AI gets some reward. That behavior is reinforced, just like reinforcement learning with like training an animal or whatever. This is the same thing we try to use to build agents that are smarter than us. It's just sort of shock them if they do something bad, and then you have some fancy names for it. There's a sort of obvious problem that if so far whenever the reward button gets pressed, it's good for the agent it's good for the agent. Maybe if you sort of just kill the user and take the reward button, you just cut out the middleman, and you could get just as much reward or more, right? So this is actually a very sensible generalization, but it's not one that we prefer. So in some sense, it's sort of not the intended behavior, but it's kind of generalization. And maybe this is a slightly ambiguous situation. Certainly, we sort of have not uniquely expressed our preferences about the reward button. Okay, so so another fun example is Goodman's new riddle of induction. So I'm not actually going to engage with this as like a philosophical problem. So this is going to be sort of one of these like computer scientists and philosopher miscommunications, where maybe take it a bit over literally. But the idea is sort of the sky has always been blue. Everyone uses this example. The clear sky in the day is sort of always blue. So we're sort of feel confident generalizing that the sky will be blue in the future, just like the sunrise. But what if the sky is actually green? So this would mean it's blue before 2035, and then it's green after 2035. So it's also been sort of green every day, right? So why not continue being green on 2035, which would then mean we predict it would become green in 2035. So that intuitively seems unlikely. But actually, the question that I'm sort of more interested in here is like what would actually convince you that the sky might turn green, other than the sky actually turning green. So obviously, if you had some sort of scientific explanation for why the sky should be expected to turn green, some detailed fact about the climate or some sort of biological organism spreading through the atmosphere or something, that would be sufficient. But actually, presumably, there's a lot of other things that would convince you that the sky might switch color that are sort of sort of unrelated to this. Like for instance, if suddenly gravity turns sideways or something, then you might your credence in a lot of things would increase. Or if someone sort of suddenly pulled you aside and told you that you're in a simulation or something, and made some very convincing demonstrations, bending a spoon with their mind or whatever. Maybe afterwards you'd be more willing to believe that the sky would turn green, just because you don't trust sort of any of your knowledge. So roughly speaking, this means like some rule that previously you thought always holds has been violated. That makes you doubt everything else that you think you're certain of. And this will actually turn out to be the case for Solomon abduction. Okay, so so enough of this. So now I'll talk a little bit about algorithmic probability, and we can. So I thought second talk it was good to define some things, but of course we already had some definitions in the first talk. But then again, I guess also some new people. So maybe I'll go through this a bit faster. But yeah, so basically, Solomon abduction is a general sequence prediction method. It's pretty simple. You just take a Bayesian mixture over programs, and that sort of are potential hypotheses for generating some binary sequence. And then as you see more of the sequence, you just like do Bayesian updating. People like to hedge a bit and say this is sort of like the basic idea of it. Actually, this is pretty much just a technically correct explanation of Solomon abduction. The only real like technical point is that the codes have to be self-delimiting for the programs, but this is already true for most programming languages. So, so this can sort of capture these problems of non-stationarity in a certain sense. So if you take Solomon induction as an objective, from an objective Bayesian standpoint, it expresses the belief that that your observations are computably generated by some distribution, and that distribution doesn't change. But the hypothesis class of all computer programs is sufficiently rich to capture computer programs that have non-stationary behavior. So it sort of includes distributions which switch between other distributions, right? So in that sense, you can capture non-stationarity, and yeah, so you can think of just, you execute one program and then sort of when it finishes, then you execute the next program. You append those two, and that's also a program. There's some compositional closure. Okay. So then I took a slightly more technical explanation of Solomon induction, which you can sort of express. So you can express with like purely deterministic programs just sort of by including the random seed as part of the program. And then rather than saying some programming language like Python, you can take a universal Turing machine to be slightly more formal. And then you get this expression on the bottom where you take the sum of all programs that could have generated some sequence starting with your observation, and you just assume that they sort of come from some random, you put sort of equal weight on all of them according to their length. So you just assume they're sort of randomly generated, like the monkeys on the typewriter thing. This is called the universal distribution. It's written M, usually. And seems like by everyone except algorithmic randomness people, it's sort of always M. And then you can think of then as you go along and you observe more observations, you condition, but conditioning is just the same as just like throwing out any programs that have been ruled out when you include the random seed as part of the program. Okay, so I think we skip this. Okay, so so my argument about sort of representing ambiguity and algorithmic probability is that M is already sort of the state of maximum ignorance. So if you take just a uniform distribution over binary sequences, that's actually a pretty strong claim because you're saying that there's no computable structure for you to learn. But if you structure your predictions of an unseen sequence according to M, you're saying any possible rule could have generated this sequence. Any rule that I could conceive of is a possibility. And you sort of spread, and also you sort of spread your weight out over all the explanations sort of as thinly as possible. Yeah, so being in sort of an ambiguous predicted situation seems like a reasonable definition is sort of returning to the state of ignorance. Um, so yeah, so the working definition is that I'll use in this talk is that the future is ambiguous at x. When you condition in a probabilistic sense on x, that's sort of the same as just like conditioning in the sense of oracleization. So there's you sort of just have access to the past, but you don't really rule any explanations out. You just give your explanations access to the history. Yeah. Okay, so definition of prefix Kolmogorov complexities. This is sort of the Kolmogorov complexity definition for finite strings. So you have some program that generates some string that halts. Yeah.
Are you going to define or rigorously what you mean by M superscript X? Like, what does it mean to not conditional but still?
That's a good question. So Turing machines have like this. So for the UTM, we'll have like a program tape, and then I'll have some output tape, and then it might also have some work tapes, right? And oracleizing on X just sort of means you put X on one of the tapes, like an extra tape or one of the work tapes or whatever. So it just has like computably has access to it can read access to X.
So it's a broader class of behavior, right? Because you can like conditioning on it forces you to use the information in a very specific way, or that builds probability.
Yes.
And have dummy input tape. You can do that, but you can also
So if you oracleize on X, if you put X on an oracle tape, you can condition any computable distribution on X. You can't actually condition the universal distribution on X because it's only lowers than computable. But that's sort of spiritually correct, yes.
But then it's kind of like a intersection. So there's stuff that you can do by conditioning on it, and there's stuff that you can do by oracleizing on it. But both of those can do things together.
Yeah, that's right.
Yes, if you just put it on the tape, but you're not saying giving any meaning to this, like saying like this is actually what happened, this is the true history up to this point, then is M oracleized on X just the same as M? Like if you're not saying that's something that should skew your prior in any way.
No, it's not the same. So if you have the reason I choose to do the oracleized version, I could have just not oracleized on it, and because you can choose to ignore the thing that's on your oracle tape.
Yeah.
So there's also so it sort of dominates in the so up to a constant multiple, it's bigger than just M. But it can also do things that you can't do without X. For instance, even if X is some humongous string, there's always if you put on the oracle tape, there's always a short program that copies it. So even if it's sort of some very complex string, you always have a lot of probability concentrated on that. So after some uncertain moment,
it's basically M, but with a different universal Turing machine, one that already includes X kind of thing. So
yeah, so it is true. Yeah, right. So it is true that M including X is a UTM. Yeah, but it's a UTM whose like complexity depends on X. You can hard code X into UTM. Okay, so we'll need the prefix Kolmogorov complexities. This is discrete Kolmogorov complexity. We'll also need the discrete universal distribution, which just mixes over all programs that could have generated some finite program. So yeah, I guess this will become apparent in a second. So for the balance, are people comfortable with these definitions? So these are like this is like a universal probability distribution on finite strings. So it's different than the sequence prediction case, but we'll use it kind of to talk about the prefixes of strings. Okay, so now we talk about what I like to call fractal structure, and I think maybe I was the first to come up with this nice name for it, and possibly yeah, and I guess to write down this sort of fractal inequality. Though there've been a lot of similar ideas. Okay, so and also of course could be wrong about this. So yeah, so the idea is if you're so the explanation for the motivation is sort of that the explanation for the past and the future could switch. We could have sort of different machines generating the past and the future, and that's when things are ambiguous. So here, I guess you should think of X as the past, and Y as the future, and in the condition, we sort of need an explanation for both the past and the future. So that's why we talk about X appended with Y. So so there's this simple sort of structural result that we could use a program to generate X, which has some finite output and then halts, and then we just like hit return and keep typing the Python script basically, and type the next line of the program instructions, and then just use some other program to generate Y. And for the program generating Y, we can use the universal distribution because we only care that it starts with Y. We don't need to like find this division point, right? Yeah, and in fact, we also can have access to X when we generate Y because it's already been written out. So this is accessible. Yeah, and then you can strengthen this by saying rather than just taking sort of one possible explanation for X, we'll just combine all the possible explanations. We'll just sort of randomly use a UTM to randomly generate something, and then once it halts, then we switch to the UTM that just continues generating the whole thing. And then you get this factor, you get the discrete universal distribution instead of 2 to the negative k of X. But actually, these are by the coding theorem are the same up to constants, so this isn't really an improvement. Yeah, so I guess I already wrote that. Yeah, okay. So then this is still actually pretty basic stuff. If you are familiar with AIT, just taking the logs, the negative logs or surprisals of both sides of those equations, you get this comparison of the Km is just defined as negative log of the universal distribution. So this is sort of an immediate consequence, but it's sometimes treated as a complexity. And this is essentially just some variation on the chain rule, which is that you can generate X and Y by first generating X and then using it to generate Y. Okay. Yeah, so this is the result is sort of fractal inequality, yeah. So the question is how much can we improve this? So we certainly cannot improve to use the M of X, so to use the universal, the continuous universal distribution for X, because we have to sort of know where to stop. And yeah, I think I forget the easiest to see counterexample, but it's pretty easy to see that this is not possible. But we can do something close. So yeah, so just sort of dividing both sides by the continuous universal distribution, we get this lower bound for the conditional probability of Y given X, which is in terms of the sort of little m over big M of X. Maybe I'll probably need to do some like Huffman coding here because I use this a lot. Maybe I'll call this the fractional complexity or so, which is yeah. So just the discrete over continuous complexity of X. Yeah. Okay. So then I make everything. So everything's an argument of Y. So if you just sort of remove the Y arguments and write things more compactly, then you get this bottom line. The conditioning on X is at least as great as fractional complexity of X followed by M superscript X. Okay, so the annoying thing about this is that this like fractional complexity measure thing is not very nice. Yeah. Oh, I only have 5 minutes. Okay, let's move quickly.
Including questions.
All right. So we'd like to quotient out the continuous universal distribution. Okay, so to do this, we use this recently defined stopping complexity, k stop of x, which is defined as the shortest program that reads x, that reads exactly x before halting. So sort of one rate reads x and then knows when to stop without looking at the future. And this can be thought of as like looking for the first time that some law is violated by a sequence. So if you see 0, 0, 0, 0, 0, 1, the first one you see tells you, oh, I'll stop here. Okay. And it doesn't matter what comes after the one. You already know it to stop when you see the one. So this is the stopping complexity introduced by Wyeth and yeah, so they use this particular prefix-free version. So this is interestingly, these are sort of complexities that live in like that we'll see sort of live in this like conditional space rather than this sort of joint space. So they're very natural sort of prediction with algorithmic probability, the sort of thing we think about in AI rather than algorithmic randomness. And it's analogous to this K star, which was introduced by Chernoff and Stringerber for posteriorization of predictive data. Yeah, so I guess some examples we'll skip. So again, we can mix over the stopping programs to get a slightly better bound for when to switch. And it turns out one of the few results in this kind of ongoing work that's actually original less is this machine that stops probabilistically is the same as a universal lower semi-computable time semi-measure in the sense of Wyeth et al., which is characterized by being bounded, but there's some sort of being bounded by one along any given sequence. So rather than the universal discrete distribution, which is bounded over all strings, it's over prefixes of the given sequence. Okay, so then we can simplify this. So noting that we can generate x with the continuous universal distribution and then stop when some stopping program tells us to. We get this inequality for the discrete universal distribution, and that allows us to simplify this fractional factor to get this sort of nicer coefficient in terms of the stopping complexity, and by the same way we could get a coefficient of the stopping probability. Yeah, and then we have some sort of nice results on, actually kind of not very nice results on the stopping probability. So far we haven't found a version of the stopping complexity where the coding theorem holds. It extended some negative results on this. It sort of, so it sort of doesn't hold for these like prefix free codes, possibly for prefix stable codes, we don't know yet. And also this factorization is not quite exact. So there's some, it's possible for this fraction to diverge along some sequence, which is studied by stuff that's been studied by Andreev, and as a context of randomness deficiency. So it's certainly not bounded by one, which means that it's so you can sort of easily, though you sort of already showed that the stopping probability lower bounds this fraction, it's the opposite's not true. Yeah, okay, and also interestingly, even with this conditional fractional sort of conditional probability of halting, the chance that the sequence ends can be higher because sometimes you can't detect whether a machine will halt. So the sort of the measure defect of the universal distribution can be greater than this. So breaking some law puts you in an ambiguous situation, but it appears breaking many laws simultaneously can lead to greater ambiguity than any individual law violation. And there can also be cases sort of where you expect some ambiguous situation because some machine sort of halts in a latent way, but you can't detect it from the sequences law as either stochastically or deterministic law violation. Yeah, so I have some further questions about whether this is tight, which I'll skip. So, yeah. That's all.